This is example 10.8 from Discovering Design with Chemistry. Over here to the side, I have included some of the formulas from this chapter about gas laws and also a piece of the chart from the book. In my book, it's page 311 because we will need that in a few minutes for the problem. So there's also a chart at the back of the book in the back cover for vapor pressure if you need it for future problems. The problem says, a chemist makes carbon dioxide gas according to the following reaction, and we have a chemical equation here that represents that. If the chemist collects 2.4 liters of the gas produced over the water in which the reaction took place at 30 degrees Celsius and a pressure of 756.1 torr, how many moles of carbon dioxide were collected? If you're not even sure where to start with this, let's start labeling things. So 2.4 liters of the gas, that's a volume. 30 degrees Celsius, that's a temperature. Pressure of 756.1 torr, that's a pressure. And then what we want the moles of carbon dioxide. If you look over here at these equations, several of them have, the two in the middle, have both pressure, volume, and temperature. But the one in the blue box really just helps us to compare the pressure or the temperature or the volume change of a system to show the relationship that when temperature increases or decreases, pressure or volume also does the same. And when pressure increases, volume decreases. So it shows the relationship between those, but it's not going to help us find the moles of anything. And this next one does have all those same numbers, plus it has an N in it, and that represents the number of moles. So that's the one we're going to be using. But we know that from other parts of the book, we have learned that we can't just use all the units just like they are. So this temperature, let's go ahead and convert that to Kelvin. All right, so when we add that, we're going to get, oh, no, so we can't keep the 0.15. It's going to round. So when we add it, and because I work with both significant figures and with adding, we could just add this in our head, but I think it's easier to make sure that you don't make a silly mistake and forget about the significant digits of something if you type it in. So 303.2, because our 30 degrees Celsius has its last digit in the tenths place. So 303.2, and that's just Kelvin. So there's our temperature. The volume's in liters already, so that one's fine. But in this particular equation, we're using ATM because if you look at the units for the R, it has liters, ATM, moles, and Kelvin. So all the other things in the problem, the P has to be in liters. The P has to be in ATM. The volume has to be in liters. The N is the number of moles, and the T has to be in Kelvin. So those different units will cancel out correctly. And so we need to change this to ATM. So 756.1 torr. And if you remember, 1 ATM, 1 ATM is equal to 760 torr. And so we can convert that to the ATMs that we need. So 756.1 divided by 760. Wow, that's really long. All right, so in this one, the 760 is exact, so we don't have to worry about that number. We just have to worry about the first one, the 7, what was it? I've already forgotten. 756.1. Oh, you know what? I totally missed something that's really important here. Before we get started on this, it mentioned that we have these two up here. There's water involved, so there's going to be water vapor. So before we can work with that pressure, we have to take out the water vapor pressure so that we're left with only the carbon dioxide pressure. We have two different things that are going to cause some gassing. So let's back up and fix that, which is like the whole point of the problem. I'm not really sure where my brain was just now. Right, so the total pressure here is going to be the pressure of the water vapor plus the pressure of the carbon dioxide. So what we can do is we can write our P of carbon dioxide, and you can write the whole word, but I will run out of room if I do that, plus the water vapor. I'm just going to abbreviate that with a WV. We know that our total pressure is 756.1 torr, And then what we want is the carbon dioxide pressure. The pressure of the water vapor we can get by using a chart in the book. And the chart is on page 311 in the book version that I have. It's also in the back cover of the book. But the water vapor pressure depends on what the temperature is. And so for 30 degrees Celsius, it's 31.8 torso. That goes here. And so then all we have to do is subtract 756.1 minus 31.8, and that will give us the pressure of the carbon dioxide in torr. So 724.3. So this is our actual pressure. This is the pressure of just the carbon dioxide. So this is the pressure that we care about. The pressure up here is just all the pressure. So we're going to scratch that out so we don't get confused about which P we're using. All right, so now we can take that pressure and turn it into the right unit of pressure. Let me use a new color because I'm getting really close with all my stuff. All right, so if we have 724.3 torr, and we want to change it over to ATM, we have to convert it. So torr goes on the bottom, ATM goes on the top. For every 1 ATM, we have 760 torr, and that 760. We're not worried about the exact. We're not worried about significant figures with that one. 4.3 divided by 760. So we just need to keep 4 significant figures because that's what the 724.3 has. So 0.9530. 0.9530 ATM. All right, so here's the pressure in ATM of our carbon dioxide. So we're going to use this one for our pressure. And then we have our temperature in Kelvin right here. The number of moles is what we're finding out. We already have R, and then volume was given in the problem. So now we have all the pieces we need to make this problem work. So PV equals nRT. All right, let's find our P. That's 0.9530 ATM. And then times our volume, which is 2.4 liters. That equals N. And R and T would normally go right here, but I know I'm going to have to divide both sides by those. So I'm going to go ahead and divide both sides by those. It will cancel out the R and the T that were over here when we divide that side. The other side is where they will end up staying. So we're going to put R down here. So 0.0821, and that's Latam over Molic. You can ignore my weird words. That's how I remember the unit. And then our temperature was 303.2 Kelvin. All right, so let's start canceling things out. It's a different color to work with. All right, so my K cancels out here because one's on the bottom, one's on the top. The liters that are on the top cancel. The ATMs cancel, and mole is on the bottom of a bottom, so that will stay and become on the top. All right, so I've got all my units worked out. If your units ever don't cancel out correctly, you probably accidentally put something on the top or the bottom when it should have been on the other, like when you rearrange the equation, so check on that. All right, so 0.9530 times 2.4 divided by 0.0821 times 303.2. Oh, and that has way too many zeros in it. All right, so my final answer is going to need to have no more than 2 significant digits because of that 2.4 liters. It's the smallest number of all the different significant digits, so I get 2, 0.092. And because that's the number of moles, and that's what they were asking for, is the number of moles, this is our final answer. All right, so the only thing that was kind of new and different about this problem, because we've done problems that involve the ideal gas law, which is this one right here. We've done problems that have needed that before, but what we had to do extra or different this time is we had to take away from the total pressure the vapor pressure of water, and we use a chart to find that number. If we hadn't subtracted out that pressure of the water vapor, we would have gotten a slightly bigger answer. It would have only been 0.096, so it's not huge, but it wouldn't have been the right answer. It's measurably different. And so and the book points out if the temperatures were greater, the effect would have been greater, because if you look at the chart, as the temperature in degrees Celsius goes higher, the vapor pressure is higher too. And so eventually it would be so high that it would take away a much bigger chunk. And so the higher the temperatures, the more mistake there is in that final answer. Anyway, so we labeled, we found what we had, we found what we needed, we found the equation that worked with that, and then we had to make sure all the units were right and all the pieces were right. And in this case, the new piece is the pressure. We needed just the partial pressure, not the total pressure. All right. Like I should circle this with a different color. I've got so many things circled on the page. And that's our final answer.